In this video, we're pitching our preliminary research into magnetic levitation trains and demonstrating that the field has sufficient research potential to deserve funding.
So what are maglev trains? A maglev, or magnetic levitation train, is a train that moves without touching the track. Instead of wheels, it uses magnetic forces to lift, guide, and propel itself. There are two types: EMS, which is electromagnetic suspension, and EDS, which is electrodynamic suspension. The main difference between the two is that EMS uses forces of traction between the train and the rail for suspension, whereas EDS uses repulsive forces, inherently making them less stable. An EMS maglev train has electromagnets mounted underneath or along its sides, tracks of iron rails, and magnets pull the train upwards towards the rails. A small gap of about 40 millimeters is maintained between the two. Sensors and control systems constantly adjust the magnetic force to keep the gap stable.
Our model uses three main equations. The first equation is Ampere's law and one of Maxwell's equations. It describes how current densities produce curled magnetic fields. The second describes the vector potential of the magnetic field and shows how it is a pure curled field. Lastly, the total current density can be expressed as a sum of the external current and material conductivity. The model we developed consists of an iron rail 1 meter in length and 0.3 meters in depth. Underneath, there is a superconducting coil of copper with an iron core through the center. The iron core and coil are connected to the train above the rail, so an attractive magnetic force will act against gravity. The entire geometry is surrounded by a 3-meter cube of air to observe the field outside the solid pieces. This model was based off a paper released by NASA called Superconducting Electromagnetic Suspension System for Grumman maglev Concept.
There are two major boundary conditions outside of the default magnetic insulation that encloses the entire model. Firstly, there's an external current density imposed on the coil of the wire. The current makes use of a second coordinate system with the origin at the center of the coil and defines a current density in the phi direction, which is just around the coil, using a value of 53 amps as specified in the reference paper. A passive conductor domain specifies that the domain can conduct currents, but that it will not produce any by itself, and instead the currents are purely from as a result of changing magnetic flux, resulting in eddy currents. To initially validate the model, a simple parametric sweep was done to ensure that the attraction force between the rail and the train was proportional to the current, which is what can be seen in the graph, with an exponential increasing force with the current in the coil.
For heating, we looked at the temperature variation in the rail due to induced currents from the coil as the train approaches. Faraday's law gives that the electromotive force is proportional to the change in magnetic flux with respect to time. The largest change in flux with respect to time will therefore be seen when the train is going at peak speed. The reference paper gives the top speed as 134 meters per second. Therefore, from the perspective of the rail, it takes 1 over 134 seconds for the coil to come into the model domain. The approximation therefore uses a current which increases from 0 to 53 amps with a slope of 53 times 134, giving that the current equals 53 at 1 over 134 seconds. Instead of using a moving mesh, which greatly complicates the model required, we instead looked at the heating effects caused by increasing the current, which approximates the train's movement. At first, the model was ran for 0.05 seconds in order to capture the extent of the relevant time frame for our stationary model. There is very little change in temperature in this time frame, indicating that the effectiveness of the model. When ran for 10 seconds, which is equivalent to a 1 kilometer long train, the temperature increases dramatically, indicating that a very long train would not be physically viable, as the changes in magnetic flux along the length would cause too much generated heat in the rail. This indicates that maglev trains are most suitable for passenger trains, as freight trains tend to range in length from 1.5 to 4 kilometers.
To investigate the stability of the train, two parametric sweeps were done where the distance between the track and the wheel is varied, simulating shakes and movements of the train along the track. The graph on the left shows as the train moves side to side relative to the track. When the rail is further to the left, in the negative direction relative to the train, the horizontal component of the force, seen in blue, increases in the positive direction, pulling the train back towards the center. The same can then be seen on the opposite side with a negative force vector. This shows that one of This shows one of the key benefits of electromagnetic suspension, where it naturally gravitates back to stability, which is important as seen by the quick drop-off in vertical pull as the rail moves further away. As the train rotates relative to the track, simulating the train tilting to the left and right, the magnitude of the force vector, shown in light blue, drops off. This shows that the train staying level is important and that the core geometry is very important since it's the only part of the model that is not axisymmetric. To investigate this effect, the claw of the core was parameterized. On the left, the magnetic flux density can be seen decreasing and the streamlines pointing further away from the rail as the claw retracts. This shows that the core geometry plays a key factor in the performance of the train suspension system. The graph reinforces this, showing an exponential increase in the force as the claw extends. One thing to notice is a high flux density getting caught in the sharp corners of the core. The impact of these corners was examined by manually filleting the inside edge of the core and parametrizing it. The streamlines can be seen to become less rounded and therefore less effective as the fillet decreases. The graph shows an increasing trend between the force and the fillet radius, but the efficiency seems to be minimally impacted. The drops in the line are likely a result of meshing or numerical issues, which shows room for improvement in the model.
The rail geometry was then also parameterized. You can see that as the rail gets thinner, there is little to no effect on the magnitude of the force up until the rail gets very thin, at which point there's a steep drop-off in force. This indicates that there is a minimum rail thickness required. In the animation, you can see that the magnetic flux is low right up until the rail reaches its minimum thickness.
Now looking at energy efficiency, the total energy is the energy stored in the entire volume, while the vacuum energy is the field energy stored in the surrounding area. The latter accounts for a large part of the energy, which means most of the magnetic field is not interacting with the geometry itself. Efficiency was calculated as the difference in vacuum and total energy divided by the total. This corresponds to the fraction of energy stored in the magnets themselves. As the gap between the rail and the coil increases, there is less energy stored in the field overall. However, the efficiency increases linearly. Similarly, for the current, increasing the current leads to a seemingly exponential increase in useful energy, which is the energy stored in the field in the volume of the magnets and the air gap. Looking at the weaknesses of the model, the resistance of the coil was integrated into the model using the material properties. This was a good simplification because it only impacts the Joule heating. In reality, the coil is superconducting and will have no resistance, so we can just remove its contribution to heating. The model was also constructed in a vacuum as opposed to being filled with air. While this could have some impact, especially at high speeds, air has very similar properties and can be approximated as a vacuum. Thirdly, the model itself does not take into account the train sitting on top of it, so the necessary current and force might vary. In the future, we could further explore the movement of people on and off the train and how the magnetic force needs to change accordingly. Finally, our geometry is based off one specific paper, and it would be interesting to explore various other setups that could produce different results. So why should you invest? Our research focuses on updating the fundamental theories behind magnetic levitation systems. Developing better computational models is the key to refining the technology. Currently, only a few select countries have maglev trains, but with further research, they can become much more widespread. By funding our research, you will contribute to improving transportation around the world.
Thank you for your time and consideration of our proposed research. And this is the paper that our research is based off of.